All right, are we back up? Sorry. Okay, so what happens here is that you can view this thing as the set of points that fail to impose independent conditions on lines. So that you see, we were somehow cheating and drawing the curves, but our conditions for these kinds of things were similar. So it just happens that if you want to find the most extremal condition when you have 12 points, right, then it's not given by a line bundle, but it's given by a higher rank bundle. So that you are forced to sort of, you can't just draw a curve and say it. Okay, so that it turns out that what you need to do in general to answer this question, and you do the following thing. Suppose that you have a vector bundle, right, such that the demand, such that you don't say that you have a vector bundle of rank R, right, rank R with MR sections. Okay, so here is my vector bundle of rank R with MR sections, right? If I ask that those sections vanish on these M points, I typically expect that each to vanish at a point to be R conditions. So since I have M points, I typically expect that there aren't any non-zero sections that vanish on those M points. So that I can look at the locus of points, right, for which that's not true. In other words, the locus of points that fail to impose independent conditions on the sections of this vector bundle. Okay. Now you see, when this thing is a line bundle, it's easier to see that this thing is a divisor because, I mean, you can play the following game. Suppose that you have, when you have a line bundle, right, each point is supposed to decrease the dimension by 1. So all you have to do is that, find a curve that's vanishing on your previous points, right? And choose a point that doesn't lie on that curve. Then that decreases your dimension by 1. But if the rank is larger, right, each time you add a point, you need to say that you decrease the dimension by R. And that turns out to be a fairly tricky problem. It's not so easy to show that this thing is a divisor. The danger being that it could be maybe all points fail to impose independent conditions on sections of this vector bundle. But if you can show that the general set of M points impose independent conditions on the sections of this vector bundle, right, then what you see is that this is a divisor. And then you see the first hope that you can have is that maybe the extremal, the most special configuration of points can be obtained this way. And it turns out that that is the answer. Okay, but now let me tell you which one it is, right? So in 12 points, I sort of pulled this out of a hat and said that, hey, I know what the answer is. But presumably most of you didn't guess this, and then even now you probably are wondering how on earth did you come up with this one as opposed to something else, right? So let me tell you what the answer is in general. Okay. It turns out that you can't look at arbitrary bundles, right? To get a good space of bundles, what you have to do is call something, you need to talk about stable bundles, okay? And what that just means is that you don't have, you don't have sub-bundles that are more positive than your bundle. So what that means is that there's a measure of this thing. So anyway, there's some technical condition that says that you look at stable bundles, okay? And it turns out that we understand the classification of stable bundles on P2, okay? It's not a simple classification. It's fairly complicated, and it involves lots of very pretty mathematics. So first of all, there are these exceptional bundles of things like, the tangent bundle or these line bundles and things like this, which are where the moduli space is a point. And it turns out that there's a complete classification of these things, and it's closely related to, the Markov equation. So there's a one-to-one correspondence between slopes of these things and the solutions of the Markov equation. And, It's a story that I'm not going to tell you, but it's really pretty. So, I encourage you to look in the story, at the story, if you're, if you want to learn about this. But, what happens is that each time you have an exceptional bundle, so here are my exceptional bundles, it turns out that the invariance of stable bundles, each exceptional bundle restricts the invariance of these stable bundles. And then if you put all these restrictions together, you get some fractal curve. So, I drew this thing a little bit. So O is here. So there's a peak over that. Then the tangent bundle is here. There's some peak over there. There's some other bundle here. But if you just, look closer and closer, this is really a fractal curve. Okay. And then the theorem of Drezeux-Lepotier says that, there exists a stable bundle with given invariance if and only if your invariants lie on or above the curve, or you're one of these exceptional things. Okay. And then the nice thing is that there are these moduli spaces, of these stable bundles. Okay. And it turns out that, you don't just need to answer what's the most special devised codimension 1 condition just on points. You can answer it for these moduli spaces all at once. So maybe let me tell you what the answer is. You look at the Euler characteristics. So you have your moduli space, it could be the Hilbert scheme of points, right? And what you do is you look at your Euler characteristic. If you look at this Euler characteristic, there is some Riemann-Roch formula which gives you a parabola in the space of invariance, right? And then what you see is the following thing. Then it can intersect this fractal curve in basically one of 4 ways. One is it can pass through this exceptional thing. One is it can go below the exceptional thing and intersect it there. One is that it can go above this exceptional thing, but intersect it on the left branch, or it could intersect it on the right branch. In which case, what you do is that you take the left branch and you take that intersection. Okay. So given your invariance, this is an easily computable thing. I mean, you can easily find what this W invariant is. It's just an intersection of 2 parabolas, and in fact, the parabolas are translates of each other, so they are just, it boils down to a linear equation. So then the theorem is like this. Okay. Suppose that you have a general member of your moduli space. So the way you should think about it is that you have general M points in the plane, right? And suppose that you take a general bundle in this moduli space, the one corresponding to the W, depending on the cases. Then it says that the cohomology vanishes, of the tensor product vanishes. And furthermore, then it means that I can define this Brill-Noether divisor. In other words, the way you should think about it is that I have the E's which fail to impose independent conditions on sections of F, or those for which H not of E tensor F is not 0. There are sections of that. And then this theorem is that that is the extremal effective divisor. So in other words, coming back down to our special points with special codimension 1 special conditions, you take this bundle that you get that I described from the classification, and the set of points that fail to impose independent conditions on that bundle is precisely the extremal configuration of M points in the plane. This theorem has many consequences for the birational geometry of these spaces, or for computing cohomology in general and things like this. But, I think I'm out of time anyway, so let me stop there.
Let's all thank Izzet for the talk. And open the floor to questions. Please just unmute your mic and go ahead and ask. I have a question that's really more just about, could you talk through the theorem one more time?
Sure, that was really fast, especially since I was gone for a while and I was distracted. So like basically what it says is the following thing. So you have the classification of stable bundles. So it's given by this fractal curve, and you can really compute these things. I mean, it's for most purposes, right? This area is really small. So like 92% of this thing is covered by like these line bundles and just TP2, okay? So that, you can sort of forget about these in between things. So what you do is you take your character, which is the character of m points, right? And you look at the Euler characteristic. So if you look at the parabola defining when the Euler characteristic is 0, right? At some point it hits the last stable bundle. And that stable bundle, failing to impose independent conditions on that stable bundle, is precisely the extremal configuration of points.
So the character, this is not a variation of stability condition.
It's not a variation.
Okay, so this is just a different.
This is just the churn like this. You just compute the Riemann row, right?
Right. Okay.
So you treat this thing as a variable. So like if I took this invariant, say that this was, I guess we say that this was u, right? So then you can compute this churn character, and then Riemann row tells you what the Euler characteristic is. So you look at those where it's 0, right? So that because I want to get these Brill-Noether type divisors, right? And then the statement for the Hilbert scheme of points is that you look at the last possible stable one. If it passes through this, it will be this, yeah? If it doesn't, if it ends there, it will be this, or if it ends there, it will be that, right? Except that, in higher rank, there is a little twist like this, which we can ignore for the purposes of this discussion, right? And then basically what this is saying is that the m points that fail to impose independence conditions on this bundle, on the bundle here, on the bundle there, or the bundle there, is the most special configuration. I mean, two statements. First of all, that there exists an effective divisor like that, and then two, it's the extremal one. I mean, like I didn't do it here, but you can actually make a list of this thing easily up to the first 500 points or something with no difficulty. The computer will spit it out in like less than a minute or something. So,
is there a similar classification of the stable bundles for other surfaces?
That's a good question. So there are very few surfaces where we understand the classification of stable bundles. So one of them is K3 surfaces. So we understand there the existence of stable bundles completely. The other place where we understand the stable bundles not as completely as the Hirzebruch surfaces. There is an algorithm that goes rank by rank that could tell you exactly what it looks like. And then the picture is somewhat similar. There's a, there it's not fractal curve, but the fractal surface, so it's even worse. And then there's the unrequest surfaces that we understand to a certain extent, and some elliptic surfaces. But modulo those, I mean, we basically don't know like, if you give me the character, like there are two types of theorems, like sort of the kinds of theorems where for the surfaces I already listed, we sort of understand exactly what are the characters of stable bundles. Other than that, we don't know in general, but then there are theorems that say that, if you make the second Chern class large enough, then there exist stable bundles and things like this. So there are asymptotic theorems that tell you when these spaces exist, and then for very special surfaces, then we have classification. The first interesting example is the quintic surface in P3, a very general quintic surface in P3. Even then, it's not known.
Izzet, could I ask a question too? This is Herb.
Sure,
Yes. So morally speaking, does the pathology of the Hilbert scheme increase with codimension in general? In other words, there's some structure, like you're talking about points on surfaces. Should the pathology or lack thereof of that kind of be reflected by curves on threefolds? And then, because the counterexample, are there counterexamples in codimension 2 of components of the Hilbert scheme, becoming reducible? Though I realize there's some becoming reducible, but
Sure,
this kind of thing supported on, whatever, a single curve. Yeah.
I think already in codimension 2, you can't do so well. I mean, if you look at the Hilbert scheme of curves in P3, basically, like, I think the theorem is that basically, like, if you write any singularity that you can define by equations over the integers, then, that will occur somewhere in the Hilbert scheme up to appropriate equivalence relation. Like, basically, already if you look at curves in P3, then anything can happen. Like, the dimensions can all be wrong. It can be arbitrarily non-reduced and all these things. What is not known, like the more maybe the one interesting question that one can ask is that, like, for instance, we don't know any non-reduced components of the Hilbert scheme of points, for instance. Like, I showed you that they can be reducible, but we don't understand how terrible they can be. Just if you look at points in P3 or points in P4 or something like that. Like, for instance, nobody knows a non-reduced component. So it's possible that, points in Pn are pathological, but not arbitrarily pathological. But I think the codimension 2 things can be arbitrarily pathological. Does that answer the question, Herb?
Yeah, thank you.
I have one more maybe quick question. Back to the extremal divisors.
Yeah.
Do you know anything about the image of the rational map defined by the other boundary divisor?
I do. I mean, so I mean, like, if you're asking what's the image of the extremal movable thing, I mean, of course, one is the Hilbert morphism, so that's not
right.
The other one is a mapped. So, the way I didn't explain, of course, how the proof of these things comes about, but it's a moduli space of Kronecker modules. Let me see if I can like this. So it's a moduli space of Kronecker modules. I mean, so what's the Kronecker module? So, what you have is, like, you have what's called a quiver, but in this case, a Kronecker quiver. So it's basically, you have two vector spaces and some number of maps between them, right? And then you look at these spaces modulo, like, the action of changing bases of these vector spaces. So, like, you can get, this way you can get a moduli space of quiver representations, right? So then there's an appropriate quiver associated to this moduli space, and it's a map to the moduli space of Kronecker quivers. Kronecker moduli space. So there's like there is a lot of moduli theoretic interpretation that goes into this that, of course, I'm completely hiding here, or like I haven't talked about bridge instability or anything at all here. So, like, right. Yes, there's a lot of things that I'm completely hiding here, but we do understand what the map is. I mean, in some sense, that's how you can prove something, because you understand what the map is.
Cool. Well, thanks again for the talk. Let's all give another virtual round of applause.
Thanks, everyone, for showing up, and sorry for disappearing for a while.
Good to see you. And instead of going out to dinner, we'll save that for the next time, whenever that may be.
All right, hopefully in the next year or so, you know.
Yeah.
All right, thanks.
All right.
Yeah.